Alright, 8.3, testing a claim about a proportion. To understand this section and the next two sections, it's going to be very important that you have a good grasp on 8.2. So if you haven't watched the videos from 8.2, I believe there are two of them, then I would strongly suggest doing that first. It's even worth watching them twice because 8.2 explains a general idea of what we need to do. If you recall back in the video for 8.2, there was even a slide that shows the different test statistics, the type of distribution, and then what type of parameter that we use for the different test statistics. Or actually, it's the test statistic we use for the type of parameter we're looking at. So if you're talking about a proportion P, then this is the formula for your test statistic. And this is the formula that I'm about to use in 8.3. So it really depends on what we're talking about, whether it's a proportion, a mean where you know the population standard deviation or not, or if you're talking about a standard deviation or variance with your test statistic. And so it's very important that you understand 8.2 before you can actually go through and learn how to use these test statistics. But once you have a good grasp on 8.2, then you should be good to go for the rest of these sections. So I'm going to read through some of these slides and kind of put my input in as I go over them. Alright, so in this section we're going to complete procedures for testing a hypothesis or claim made about a population proportion. So that is made about P, the population proportion, not P hat, P. Alright, the difference in P and P hat, P is the population proportion, P hat is a sample proportion. Okay, so if you have a sample of data values and you get a proportion from that, that's your P hat. P by itself is the population proportion. Alright. Now there is two different ways to look at this. The p-value method, well, I kind of consider the p-value method and the traditional method together, even though it is two different methods because they're very similar. But the use of confidence intervals is another way, and we're not going to go over that. So we're mainly going to focus on the p-value method and the traditional method. And as long as you don't have to use technology to get the p-value, it's not too bad just to use the p-value method every time. But if you don't have the technology to find the p-value method, you may want to search online and look for p-value of a test statistic, whatever type you're looking at. If it's a t distribution or z distribution, there are formulas, or there are websites that have calculators that will do it for you. The TI calculators that do them. But anyway, I'm going to move right along to this is the basic methods of testing claims about a population proportion P. Okay. Again, we use the same notation with N, the number of trials, or the sample size. P hat is that sample proportion you can get. Just P by itself is the population proportion, and then Q is 1 minus P. Alright, so if we know that we are testing a claim about a population proportion, then we need to have a simple random sample, and the condition for the binomial distributions is satisfied. N times P has to be greater than or equal to 5, and N times Q has to be greater than or equal to 5. Alright, so you can test that pretty quick. You have to know what your population proportion is, but N times P, N times Q, as long as they're both greater than or equal to 5, then everything's good. Alright. Now, the actual test statistic that we use for a population proportion P is this formula here. This is our test statistic. This is our Z. And it is a normal distribution. So P hat, that is the proportion you get from your sample, minus the population proportion P, divided by the square root of P times Q over N. So usually what I do, if you say P hat minus P and write that down, a lot of times that's not too long of a decimal, but this right here will be, because anytime you take the square root of something, more than likely it's not going to come out to be a whole number, more times than not. So p times q divided by n and then take the square root, that number is going to be more than likely a really long decimal. So what you can do is work out the top, work out the bottom, and then divide, or you could work out the bottom first and then take the reciprocal of it, and that'll give you what you're supposed to have down here, and you could say that times what you get from the top. If all that seems confusing, then just plug in the numbers and work it out like you know how to. Don't worry about trying to do anything too fancy. And we do use table A2. That's that same z-score chart that we've been using all along for the p-value method or for the critical value. Alright, don't confuse the p-value with a proportion p. Of course, they look different. They are different. The p-value is calculated, and I would always use the table. There's a table that tells you how to get the p-value, the steps to go through. The proportion p, that's a population proportion, so they are different. Alright, it says computer programs and calculators usually provide a p-value, so the p-value method is used. If technology is not available, see figure 8.1 in the text. Alright, and so figure 8.1 is that really good table that tells you how to calculate the p-value. So I'm going to pull that up for you real quick. And again, I believe that was covered in 8.2 pretty thoroughly. So here is the table I was talking about. It's in your textbook. And so first we have to figure out, is it left-tailed, right-tailed, or two-tailed? And so you remember how to do that? Hopefully you do. If not, you just look up here. So we look at the null and alternate hypothesis, or we first calculate that. Well then, if our h sub 1 has a not equal to sign in it, then it's a two-tailed test. If we have a less than sign, it's a left-tailed test. And if we have a greater than sign, it's a right-tailed test. That's a little bit different from the previous chapters. So make sure that you look at that very carefully, figure out what type of test, what type of tailed test you had. You have left-tailed, right-tailed, or two-tailed. Once you know that, of course that comes from your alternate hypothesis, then this table tells you how to find the p-value. If it's left-tailed, go this way, right-tailed, go this way, two-tailed, go down. And what's the difference? If it was left-tailed, the p-value is going to be the area to the left of the test statistic. So you have to have that test statistic, that z equals and that new formula. And then the area to the left of the test statistic in your z-score chart will be your p-value. If it's right-tailed, it's the area to the right of the test statistic. And then if it's two-tailed, you have to know, okay, that test statistic, is that on the right side or the left side of the center of all the data? And so left side is twice the area to the left of the test statistic, and if it's to the right, that's twice the area to the right of the test statistic. So you do have to know the test statistic, and then you have to figure out left-tailed, right-tailed, or two-tailed, and just follow this chart. And you can pull this chart up during your homework or test. So that's on page 389 of your e-text. Alright, so critical value method. Use the same method as described in figure 8.2. And so let me pull that figure up for you. Sorry about that. And this figure again is from section 8.2. So if you don't have a strong grasp on that previous section, you can stop the video right now and go back and watch those videos and skip over the parts you don't like, but I'm sure you like it all. So it's very, very important. It's almost impossible to do this chapter without that. That section 8.2, known really good. And so Here's figure 8.2 that takes us through the critical value method. And it just tells you step by step how to do the critical value method. And that's, I guess, the more traditional method. Again, personally though, if I can use the p-value method, it just seems a lot faster. I'm not going to do the confidence interval method. Again, I really prefer one of those two for sure. Alright, here's a little caution here. When testing claims about a population proportion, the traditional method and the p-value method are equivalent, and they will yield the same results since they use the same standard deviation based on a claim proportion p. However, the confidence interval uses estimated standard deviation based upon the sample proportion. Consequently, it is possible for the traditional and p-value methods may yield a different conclusion than the confidence interval method. So that's another reason why these two methods give you the same, the p-value and the traditional, so I'll stick with those, and I'll let somebody else use this confidence interval method. It says a good strategy is to use the confidence interval to estimate a population proportion, but then use the p-value or traditional method for testing a claim about the proportion. So I agree there. All right, here's a little example here. I work a lot of examples in the practice test review, so I won't go through too many of these. Based on information from National Cybersecurity Alliance, 93% of computer owners believe they have antivirus programs installed on their computers. In a random sample of 400 scanned computers, it's found that 380 of them, or 95%, actually have antivirus software programs. Use the sample data from the scanned computers to test the claim that 93% of computers have antivirus software. So the first thing we need to do is go through and see what's been given. Make sure that it meets the requirements for this type of test. And so it said we had 400 computers. We need to know what P is equal to. The claim was that 93% of computers have the software. And so that makes our P, our population proportion, 0.93. And so that makes Q 0.07, because 1 minus P is equal to Q. And so you need to find N times P and N times Q and make sure they're both greater than or equal to 5. And you see they are. After that, then you need to figure out the original claim. So then you can write down the opposite of the original claim. So we already said that the population proportion, which is our original claim, was 0.93. So P equals 0.93 will be the original claim. The opposite of that is not equal to. So we have equal to and not equal to. Then our null hypothesis is going to be the one with equality, and our alternate hypothesis will be the one that's left over. So the one with equality that has equals is 0.93, and then not equals would be the alternate hypothesis there. Okay. Then we have an alpha of 0.05, and we need to calculate our test statistic. So our test statistic, P hat, this right here, this comes from the sample that we have, that 380 were found to have the antivirus software. So 380 out of 400, that's P hat. Population proportion comes from the claim, that's 0.93, and then just plug in all your numbers and work that out. It's a good idea to take your calculator now and see if you're entering in your information correctly, and you can get 1.57. Because, you know, if you just mess up with one little thing, I'm sure you know by now that that could mess the number up. So maybe practice trying to put this in your calculator till you get 1.57. It'll be a good idea. Okay, and so this thing is two-tailed. Remember, one of the criterion for two-tailed, it said if the alternate hypothesis has not equal to, and this does. If you remember, our alternate hypothesis has not equal to, so it's two-tailed. So in that table or that chart, if you follow it, that tells you it's going to be twice the area. This is a positive z-score, so this z-score is on the right of the center. So it's going to be twice the area to the right of 1.57. And so z equals 1.57. If you look that up, that's going to give you, actually, if you look it up in our table, since our tables are left to right, we'll get all this area right here. And so you'll need to say 1 minus all this area right here, and that'll give you this area right here. Once you have this, you should have 0.0582, and you say twice that. That's the p-value. So here's the p-value, 0.1164. Alright, our significance level was 0.05. So since this is greater than the significance level, you fail to reject the null hypothesis. If it was less than 0.05, then we would reject the null hypothesis. But since it's greater than the significance level, we fail to reject the null hypothesis. Alright, now that's the p-value method. That's the one that I prefer. You can do the critical value method. The first couple steps are all the same. You have the same test statistic, the same null hypothesis. And so what happens with it, you have to figure out your critical value. If you know your critical z value, then you know where your test statistic is located. Your test statistic is not located within the critical region, is it? Here it is right here. It's not located in this critical region. If it was, then we would reject. But since it's not, we fail to reject the null hypothesis. All right, I usually don't go through the confidence interval method, but you can read through that if you want. Okay. So that's all that I go over in this section. What is the main thing for this section? It's that we have the parameter population proportion, P. And so when you deal with a population proportion P, you have to use this as your test statistic.